Okay, this is a more ambitious outline than I think we're going to get to today, but it is maybe a good point here, beginning of 8th week, to look ahead, touch base with where we're at, and where I think we're going to go the rest of the quarter. Realistically, most of today is going to be spent on topics 1 and 2. I have one more thing I want to say to wrap up our discussion of mixed strategies and mixed strategy equilibria. I have a fairly small point that I want to make about representing sequential play, sequential games in normal form. Okay, so using a game that has sequence, but representing it as a matrix of payoffs. Most of the time, as I've said, you won't want to do this, but I'm going to show you how to do it because it's going to help me make clear a point I've been hinting at all along, which is that Nash equilibrium and rollback equilibria are similar. They're intimately related, but they're not exactly the same thing. Okay? The last major topic that we'll cover in the class is repeated games, and that's something that we'll do. Hope that we start it Thursday. It'll take us up to the end of class. That's our last major topic. Where we are in the book is we've been doing mixed strategy equilibria, which Dixit and Skeeth spread out over chapters 7 and 8. Okay, so you should have gone through chapters 7 and 8 at this point. If you look at the syllabus, there are some sections in section 7 in particular that are topics that we're just not covering, so I let you know what sections are not relevant there. This bit that we're going to do at the end of class today on sequential play in normal form, this is chapter 6. So I kind of went slightly out of syllabus order, out of book order here. Most of chapter 6 is easy stuff. Chapter 6 is one of the, I was going to say one of the easiest chapters. Chapter 6 does not introduce a lot of new material. Okay? So if you're feeling like you'd like some reinforcement for the topics that were covered in chapters 3 and 4, chapter 6 ties a lot of it together. Okay? So there's some sections in chapter 6 that I won't go through, but that nonetheless will help you solidify what you've learned. The only part of chapter 6 I am going to do in class is going to be the topic of sequential play in normal form. Okay, so if you were thinking, gosh, it seems like she didn't do much chapter 6 so far, you're right. What I am going to do is going to be today. Okay. When we get to repeated games, I'm losing touch a little bit with my memory of the chapter numbers. I'm pretty sure that's chapter 11. Okay. Our treatment of repeated games is going to be exclusively about the repeated prisoner's dilemma, but you'll see even with just focusing on that one game, there's a lot for us to do. Okay. Final preliminary remark is that I'm going to have to change my office hours again today, but not as much as I did last week. Today I'm going to move my office hours up 1/2 hour. They'll be back to the same on Thursday, and then I think my Tuesday office hours will also settle down. Tuesday, 1 to 2 instead of 1:30 to 2:30. I'm going to have to leave at 2, but I'll make sure I'm there by 1. Okay, so come early if you need to see me, and you can. If you need to see me after 2, send me an email or come on Thursday. All right. So moving that up, this down, first thing I'm going to do is put our same old version of Cops and Robbers up here. I'm going to do it quickly, but we need it up here because we're going to need to compare it to some other stuff. Okay, so this is Cops and Robbers, version 1, the version that we worked on all last week. We have Cops, they can be on the beat, they can be in the donut shop. We have robbers here. They can be working. They can be at home. Payoffs to -5. Watch me on this. I've messed it up in recent memory. Make sure I'm getting these payoffs right here. -5, 5, 5, 0. As we discussed in great length last week. Yikes. This game has no equilibria in pure strategies. There's no single cell where neither player would have regrets. It has a mixed strategy equilibrium where the cops are on the beat with probability 1/2. They're in the donut shop with probability 1/2. The robbers are at work with probability 4/11. I'm using the same variables as I used last week. It's all review. They stay home with probability 7/11. Okay, so the probability that we're in this cell is 4/22. Same here. Probability we end up in either of these cells is 7/22. Okay. So the last thing I want to look at is I want to use this game. I want to change it to ask some questions about what does it take in this game to reduce the amount of crime. Okay? Maybe one thing to do before we switch to the new game is to ask ourselves, what is the probability in this game, in this equilibrium, that crime is committed in equilibrium? What fraction of the time should we see crime? Eight out of 22? Yeah, that's right. What Kenyatta said is what you did was you added the probabilities in these two squares, right? Okay, so there's two of these squares that correspond to the robbers committing crimes. It happens here, it happens there. I did a pause because what I had done is I just looked at the number up here. It's either 8/22 or that reduces to 4/11. But this is the probability that crime occurs. This is the kind of question that falls into the category of interpreting a game. It's the kind of question we ask ourselves after we found the equilibrium because we need to know the equilibrium probabilities to calculate that. Okay? So 8 out of 22 days, 4 out of every 11 days, we're going to see crime. Sometimes the crime will be detected. Sometimes the crime will be punished. Sometimes the crime will be gotten away with. But right now we're just thinking about crime in general. That's the probability that it happens in this game. So what we might ask ourselves is, what is the effect of worse punishment? Okay? That you want to deter crime. One thing that will sort of leap to mind is punish those bad guys more. They get caught committing a crime, really give it to them. Okay? So what I'm going to do here is I'm going to put a new version of Cops and Robbers, abbreviating here, Cops and Robbers version 2 here, where all the payoffs are going to be the same except for this one, okay? This is the punishment, okay? This is the punishment. This is what the bad thing that happens to the robbers when they're committing a crime, and because the cops are on the beat, they get caught, okay? So we're going to make that worse. We're going to double their punishment. Give them -10 instead of -5. Everything else is going to be the same, okay? 0, 2, and make sure, again, audit me that I am actually copying these numbers correctly. Okay, so now we've got a different payoff here. One different payoff. We're going to have to look for a new equilibrium because it's a new game. We change a payoff, it's a new game. So let's look for the mixed strategy equilibrium. As before, I'm going to let Q equal the probability robbers are at work. Okay, same as before, and that's actually, I'm starting with this because this is the one we care about, right? This is the part of the mixed strategy equilibrium that's going to tell us what the probability of crime is. As before, we find Q by finding the value of Q that is going to make the cops indifferent between their pure strategies. And let me, in the interest of completeness, put the cops' 2 strategies up here again. Okay, so cops can be on the beat, they can be at donuts, robbers, work, or home. Okay, so doing this right the way I did it before. To find the robber's equilibrium probability, I look at the expected utility of the cops. The expected utility of the cops of being on the beat is, if I'm the cops and I'm on the beat, my expected payoff is 2, the payoff I get from when the robbers are at work, times the probability the robbers are at work, plus 1, the payoff I get when the robbers are at home and I'm on the beat, times that probability. Okay, cleaning this up as I did before, 2Q minus Q, it looks like Q plus 1. Expected utility to the cops of being in the donut shop. Expected utility of playing this strategy as a function of the robber's probability is -5, my payoff if the robbers are at work, times Q, the probability that the robbers will be at work, plus 5, my payoff from being in the donut shop when the robbers are at home, 1 minus Q. Okay, it looks like 5 minus 10Q. Is this looking familiar to you guys? Yeah. Want to say the punchline? It's the same numbers, okay? And it should be the same numbers, right? This is the same exact, if you go back and look at your notes, when we first solved version 1, we went through exactly this logic. We wrote down exactly these equations. We're doing it right both times because the robber's mixing probability depends on the cop's payoffs, and I haven't changed the cop's payoffs, okay? In terms of the cop's payoff, version 2 is the same as version 1. Okay? The probability of crime is still going to be 4/11ths. I've just changed the robber's punishment. I haven't changed anything to do with the cops. Okay? And the equilibrium probability of the robbers doesn't depend on the robbers' payoffs. Okay? I've been emphasizing that all last week because that's weird, right? That's the strange thing about mixed strategy Nash equilibria. And what I'm showing you here is it's not just that it's strange in an innocuous way, it gives us a counterintuitive result. Okay? When you're in a situation where players are playing mixed strategies and you change one player's incentives, you're not going to change his probability of action. Okay? Now you are going to change the other player's probabilities. Okay? So let's go through the other half of the Nash equilibrium calculation here. The robber's payoff is the same, but let P equal the probability the cops are on the beat, same as before. Now, P has to be the probability that makes the robbers indifferent between their two pure strategies. Okay? So, looking at that, the expected utility to the robbers of being at work is, now we've got a new number here. Okay? This is the number that's different between the two games. It's -10, the payoff I get when I'm at work and the cops are on the beat, times that probability that the cops are on the beat, okay, plus 5, the payoff I get when I'm at work and the cops are in the donut shop, times 1 minus P. Okay, so prettying that up, now I'm going to get 5 minus 15P. Right? Okay. Expected utility to the robbers of being at home. This remains the easy case. I get 0 either way here, so it equals 0. So setting these two equal, just as I did before, because the only way the robbers are going to be willing to play a mixed strategy, the only way a mixed strategy is going to be in equilibrium for the robbers, the only way the robbers won't regret playing a mixed strategy is if neither of their pure strategies are better than the other one. If these two expected utilities aren't equal, then the robbers can do something better than flip a coin. If the expected utility of being at work is higher than the expected utility to stay home, and I'm the robbers and I flip a coin, I'm not in equilibrium because I would have done better by picking the better choice. I'm only going to be willing to do the mixed strategy when these two are equal. Okay, so let's set them equal. The expected utility to the robbers of being at work equals the expected utility to the robbers of being at home. Just saying what I'm doing and now plugging in the numbers. This expected utility of work, 5 minus 15P, has to equal 0. Sounds like P equals 1/3. Okay, so the news gets worse. I'm increasing the robber's punishment. It doesn't affect the amount of crime that's happening at all. Okay, it doesn't affect the probability of crime, and it makes the cops less likely to be doing their job. Okay, over here, the cops were on the beat with probability 1/2. Now, in order for things to be in equilibrium, the cops are only going to be on beat 1/3 of the time, and they're going to spend 2/3 of their time in the donut shop. The robbers are doing the same amount of working and staying home. So the amount of total crime is undetected, is unaffected. The amount of total crime is the same, and the amount of undetected crime, the amount of crime that is gotten away with, is actually higher here. Okay? If we put the frequencies in the cells now, what's the probability that they get away with crime? Well, it's the probability that they commit crime and the cops are in the donut shop. 8/33, okay, which is indeed a bigger number than 4/22 there. The probability of crime that is caught by the cops is 4/33. I'll just round out the calculations here. 7/33 of the time, cops are driving around bored, robbers are at home, and 14/33 of the time. Is that adding up correctly? Yes, it does. 14/33 of the time, the cops are in the donut shop and the robbers are at home. Okay. So that is a strange thing about this game, and it is a strange thing that is true about any situation that's going to fit the cops and robbers model. These situations where there's a unique mixed strategy equilibrium, you don't change a player's behavior by changing their payoffs. That's different than any other part of game theory. Okay? When there's only a mixed strategy equilibrium and you change one player's payoff, you change the other player's mixing strategy, and it varies in context, but in most of the contexts I could think of, changing one player's incentive causes the other player to change their behavior in a way that compensates for it. Okay? So policy changes that make sense in situations that would involve sequential strategic interaction or situations where there would be a pure strategy Nash equilibrium can backfire when players are playing mixed strategies. Okay? Okay. So if I want to deter crime, what should I do? Yeah?
Does the cops' utility, like of being in the donut shop, not matter at all?
The cop's utility of being in the donut shop is exactly going to be the key. Okay? So you're thinking if we want to change the robber's payoff, then the robber's behavior, excuse me, we need to change the cop's payoff. Okay? So we could actually change either payoff. We could have, if what we were trying to do is affect the cop's behavior, we could have changed either of the robber's payoffs here. What am I going to do here? What's the example that I have in the notes that I'm going to post? Okay, what I'm going to do here is rather than, one thing you could do, I think, is you could give the cops bonuses for being on the beat. What I'm going to do is I'm going to make it worse for the cops if they get caught in the donut shop. Okay, so their supervisors are going to go around and monitor them. And what I'm going to do is I'm going to do this on a different board real quick here. Okay, so last version, cops and robbers. Cops and Robbers version 3, we're going to keep now the robbers' payoffs from version 1. Okay, we're not going for those really over-the-top punishments here. Negative 5 and 5, 0 and 0 from the same strategies. Okay, and we're going to leave, as we did before, the cops payoff from 3 of the possibilities the same as in version 1, but now, as I said a minute ago, if the cops are in the donut shop, that's really, really bad for them. Okay, they're going to get fired if the robbers go out and rob people and they're in the donut shop. Maybe the waitress in the donut shop is wearing a wire. She's going to catch these cops, and that's that. All right. So in this version, is this change to the cop's behavior? Is this going to have a... Okay, I can't ask it because I just answered it. The change to the cop's payoff is not going to affect their behavior, right? Go through the same argument that we did here. I'm changing the cop's payoffs, but the cop's decision of whether to be on the beat or in the donut shop or not doesn't depend on their payoffs. It depends on the robber's payoffs. Okay? So in this game, version 3, you don't even have to work it out. You can just look over there. What is the probability that the cops are going to be on the beat? It's 1/2. That's exactly right. Okay? The cop's probability of being on the beat, okay, this one, remember how we derived it here. We started to derive it here. The cop's probability of being on the beat depends on the robber's payoffs. Okay? The cop's probability of being on the beat is the one that makes, no, excuse me, I'm pointing to the wrong place. The cop's probability of being on the weak, I'm saying the right thing, but I'm pointing to the wrong place, is the probability that makes the robbers indifferent. Okay? Right? If I'm the cops, I'm being on the beat, that probability has got to be the one that makes the robbers just indifferent between being at work and being at home. Okay? That's how we find my probability. Okay? So the numbers that go into that are -10, 5, and 0. It's these, the robbers' payoffs. The robbers' payoffs here are exactly the same as in this game. Okay? So in version 3, the cop's behavior isn't affected. Okay? So there's kind of the weird side of version 3. If instead of asking how to deter crime, I asked how do you make the cops do their job, increasing their punishment from not doing their job doesn't do the trick. Okay? Because they're still going to, all you change is the cops' punishment. That's not going to affect their behavior. But in this case, it will affect the robbers' behavior. So let's look at that. Okay? So let's look at using blue for this. Just as above, let Q equal the probability robbers are at work, and this is the probability that has to make the cops indifferent between their pure strategies, and that's going to change now because one of the cops' payoffs is different. Okay? So the expected utility of the cops now of being on the beat depends on Q. It's 2Q plus 1 times 1 minus Q, Q plus 1, same as it's always been. Well, that's fine because I didn't change either of these payoffs. The expected utility to the cops of being in the donut shop now is -10 Q. I get -10 now with probability Q because that's my payoff when I'm eating donuts and the robbers are at work, plus 5 times 1 minus Q. Okay, so -10Q minus 5Q, yeah, -15Q plus 5. Okay, setting those equal, setting the expected utility of the cops of being on the beat equal to the expected utility of the donuts, Q plus 1, -15Q plus 5. 16Q equals 4. Q equals 1/4. Okay. 1/4 is indeed less than 4/11, so this does decrease crime. And by decreasing crime overall, it also decreases the probability of undetected crime. Okay? So if what you're concerned about in Cops and Robbers version 1 is either the total amount of crime that's going on or the amount of crime that's being gotten away with, the way to change that is to change the cops' incentives. If you want to look at it from the other point of view, if what you're really concerned with is the amount of shirking by the cops, total, the amount of time the cops are spending in the donut shop, if you're concerned about, you're the cops HMO and you're concerned about obesity among the cops, you want them out of the donut shop, or you're concerned with the amount of time they spend in the donut shop when there's crime going on. If you want to attack either of those things, then the way to do it is to affect the robbers' payoffs. Okay. So the homework you have this week is going to take you through a different scenario, but one that's going to have the same flavor to it. And what you're going to see is the same counterintuitive aspect of mixed strategy Nash equilibria. What you're also going to see is that it happens only as long as the payoffs are in the range that we just have a mixed strategy Nash equilibria. If I change the payoffs enough in this game, I'll change it to a game that doesn't even look like cops and robbers at all. Okay, I'll change it to a game that actually does have a pure strategy Nash equilibrium. Okay, so if you don't want to, I don't want to oversell this point. I don't want to say that any change in a game with a single mixed strategy Nash equilibrium is always going to have this kind of counterintuitive effect. It's going to affect the opposite player, not the person whose incentives are changing, but the other person they're playing against. That's only true as long as we're still in a situation where both players have an incentive to be random. Okay? If you change the payoffs enough that one of the players loses that incentive to be random, either you create a dominant strategy or you just create a pure strategy Nash equilibrium, then you're back in the world that makes a lot more sense. Change the robber's payoff, you change the robber's behavior. Okay? So it's only in the range of mixed strategies that we get this kind of down the rabbit hole effect. Okay. All right. Going once, going twice on cops and robbers. You guys are done with cops and robbers. All right. Questions? While I'm erasing, I'm going to start segueing into this question of representing sequential games in this form, representing a sequential play as a matrix of payoffs rather than a tree. I am going to do that. While I'm erasing, though, let me talk about what I'm not going to do, but what is covered in Chapter 6 and what you guys do need to be comfortable with. One thing you might be thinking about is changing a game from sequential to simultaneous or vice versa, right? That is changing the actual situation, not just the representation of the game. Okay? That's going to affect the outcome. So a great source of practice problems for you guys to do, you can get a lot of practice problems out of this, is take the sequential games that we went through the first part of class, okay, the ones I did in lecture, the ones that you did on your homeworks, the one on the midterm study sheet. Assume that they're all simultaneous now, okay? Set them up as simultaneous games, look for the Nash equilibrium. They will be different games, and in most cases you will get different answers. It's possible you'll get the same in, you will get the same in some of them, but that's because of the payoff. It's not because of any regularity, okay? So what I'm saying here is changing a game from a sequential one to a simultaneous one, or changing it back. Okay, so I only said half of what you could do for extra problems. You could take those sequential games, say what happens if they play simultaneously, set those games up as simultaneous games and look for the Nash equilibria, and you'll have a whole bunch new equilibria to find. They'll be different. You can also, for the stuff we've done since the midterm, all of these simultaneous games we've done, you can look at as sequential games. Suppose one player gets to move first. And here you have even more problems to do, because you could say, suppose one player gets to move first, suppose the other player gets to do first. In any of the games where the payoffs aren't completely symmetric, you've actually got two different sequential games that you can consider. They're all different. Okay, so slowing down my erasing here, making this point, but the point I'm belaboring is that when you change a game from simultaneous to sequential, that's a big, meaningful change. Okay, you're saying something different about the strategic situation you're studying. Okay, in a sequential game, if you say it's sequential, what you're saying is that the second player can condition, I'm going to get your question 1 second, can condition their choice on the first player's move. Okay, so if I'm the second mover, I get to see what you've done. That changes strategy in an important way. Okay, when you say it's a simultaneous game, what you're saying is I have to make my choice before I know what you're going to do. Okay, so same thing there. These are meaningful differences. So changing from simultaneous to sequential is changing strategy in a way that you wouldn't necessarily expect the answer to be the same. Yeah, Kyra. Kyra points out that with nature nodes, it can be trickier to change. It's not quite true that you can't change games with nature nodes. And actually, I think for the nature nodes we did this year, you always can. Okay? When a nature node is the very last thing in a tree, okay, so let's just say we have, I'm not going to draw the full thing, but I have player 1 moving, player 2 moving, and let's say that there's a nature node that's associated with just one of player 2's payoffs. Think about what's the first thing we do when we solve a sequential game. The first thing we do is we replace the nature node with the expected value, okay? And you could put that expected value as a payoff in a game matrix, okay? Your point is well taken in that if you have nature nodes farther up the tree, then that gets a lot harder to represent. And I'm not even sure if it makes logical sense when you have those kind of nature nodes to think about things happening simultaneously. But this particular kind just use an expected payoff there. One of the things that I haven't quite emphasized, but it's worth emphasizing, I'm glad it's come up, is that once you have an expected value, the fact that it's an expected value and not a regular payoff that you're going to get with certainty doesn't matter. Last week when we talked about evaluating mixed strategy Nash equilibria to see if they were Pareto optimal or not, I said just calculate the expected payoffs and then compare them to all the others. And once you start comparing them to all the others, it doesn't matter that they're expected values. Really, that's what we're trying to do with expected values. We're trying to get something that we can compare to certain values. Okay? And so same thing here. If we can do the expected value calculation, we can put it into a game and just compare it as though it was a regular payoff. Okay? And that certainly expands our ability to use game theory, the ability to use those expected values all over the place. Okay. So changing from sequential to simultaneous play changes the game, changes the result. What I want to do now, though, is a smaller thing. I want to take a game that is sequential and I want to represent it in normal form. Okay? Most of the time, you're not going to want to do this. As I said at the beginning, I'm doing it because it's the best way I know to show you guys a point I want to show you about Nash equilibrium versus rollback. Okay? So what game am I going to do here? What sequential game am I going to represent in normal form? Okay, I'm going to go back to your first problem set, first and second problem set. Okay, this is the superintendent, right? Remember him, and he wants to have his unqualified crony picked as principal over somebody who's actually qualified. There's a community leader who does not want this crony running the schools. The community leader can conduct a publicity campaign or not. Publicity campaign or not for either type of choice here. And I think what I'm doing here, I didn't write down what specific version of the problem it corresponds to, but I'm pretty sure it's the very first one that you did, where the superintendent's values was were 5 from the unqualified principal, 0 from the qualified one. So 5 is the value of getting my buddy a job compared to 0 for some person with a PhD in education. What do I care about them? But -7 for the publicity campaign. I have to run for office. I don't like people campaigning against me. The community leaders' preferences were a 0 for this crony running the schools. That doesn't look right. Can't be a -8 for the qualified. Is that right? Doesn't make sense. Does anybody have that problem handy? What the payoff here for the community leaders? Okay. I'm going to go, well, somebody's looking up that number for me. 2 is, that just doesn't fit with what I'm doing. That's what it is. Thank you, Tiffany. That makes sense there. Right. -8 for the unqualified one and 0 for the qualified one. This is the scenario, thank you, where the community leader wants a qualified principal and the superintendent doesn't. And the last part of that is the community leader costs them -4 to do the publicity campaign. Okay, so if we have the unqualified candidate and a publicity campaign, the superintendent has 5 from the kind of principal she likes, but -7 from that publicity campaign. If you've got your, I know several of you guys got out your homeworks here, so follow along and make sure I'm getting this right. So the superintendent's payoff here is -2. The community leader's payoff is -8 from the unqualified guy and -4 from the publicity campaign. Sounds like -12. Okay, is that right? If we have the unqualified guy here and no publicity campaign, that's a payoff of 5 for the superintendent. I get my guy, no publicity campaign. It's -8 for the community leader. Over here, if the superintendent picks a qualified principal and there's a publicity campaign, oh, it's terrible for me if I'm the superintendent. I didn't get to hire my friend, so he's mad at me, and there's a publicity campaign against me too. -7 there. From the community leader's point of view, it's like, okay, at least we have a decent principal, but we've got the cost of a publicity campaign to bear. And here, the qualified candidate, but no publicity campaign, gives the superintendent a 0. Okay, no plus here, but no minus there, and a 0 for the community leader as well. Okay, so that should look like the first version of this. And just strolling down memory lane for a minute, and solving this through rollback the way we did before. If we get to this branch, the community leader would rather have -8 than 12, so she'll choose not. If we get to this branch, the community leader would rather have 0 than -4. She'll choose not. Strategic equivalent here is 0, 0. 5, -8. There, superintendent says, well, I can get 5 from my unqualified crony or 0 from the qualified guy. I'll go with my crony. Okay, so the rollback equilibrium here, I'll write it out in detail is superintendent chooses unqualified, community leader chooses not if unqualified, not if qualified. This version of the game had sort of a grim moral to it, not an unrealistic one. This is one where the community leader really was not able to exercise any kind of meaningful threat over the superintendent because the superintendent knew darn well that the community leader was not going to conduct the publicity campaign. The community leader in this scenario didn't get any extra benefits from the publicity campaign, just had to go to the effort of it. Okay, so there's no deterrence going on here, unlike other versions of the game. Okay, but we're just going to stick with this simple one here. All right. So what I want to do now is I want to represent this scenario in a normal form. Okay? And what's going to be weird about this is we're going to have to get the strategies right. In a lot of ways, sequential games are easier than simultaneous games. They don't have multiple equilibria, don't have mixed strategies, at least not the ones that we're looking at. But they do have these complicated strategies. In simultaneous games, strategies have been really simple, right? Remember the problems that we did at the beginning of the quarter that involved strategy counting, right? I asked you to list all the players' strategies. And here's something where we actually might make use of that. If we say, what are the strategies? Not the equilibrium strategies. All the strategies. For the superintendent, there are 2 strategies. For the community leader, there are 4, right? The community leader strategies are PC if unqualified, PC if qualified, PC if unqualified, not if qualified, not if unqualified, PC if qualified, not if unqualified, not if qualified. Okay, remember that? The strategies in a sequential game have to tell the community leader what to do, not just at the node that we expect to happen, but at every decision node. Okay? The equilibrium strategies have to tell the community leader what to do on the equilibrium path and off the equilibrium path. Okay? So we have 4 total strategies. If we want to represent this game as a matrix, we have to have all 4 strategies in there. Okay, we have to have all 4 of these different strategies. So this is how we're going to do it. Superintendent, let's make them the role player. Their strategies are easy. Unqualified. Actually, I'm going to do qualified on the top here just to make it match the way I wrote it here. Qualified here, unqualified there. Okay. So 2 rows, 2 strategies, but I'm going to need 4 columns. Okay. I need 1 column for each of these different strategies here. Okay. So the community leader strategies, 1 is PC if qualified, PC if unqualified. Here's PC, PC. We have, actually I'm going to write them out here. I know I'll mess this up if I don't. Okay, so I'm writing PC if qualified, PC if not qualified. Here we have PC if Q, not if unqualified. Okay. Here we have not if qualified, PC if unqualified, and we have not if not if qualified, not if unqualified. Okay, now I realized as I was writing this that I switched the order here, right? Here I was using the unqualified node, or the unqualified branch, to be the first part of the strategy and not if the second. You guys see that I'm just, do you see that what I'm doing doesn't change what I'm representing? It's just the order. Okay? That these are the same four strategies. I'm just listing the qualified part first. You can tell if you see or not. Okay? So the thing to see is that this is PC if qualified, PC if not. That's this one. PC if qualified, not if unqualified. That's this one. Okay? It doesn't matter. I'm doing it this way because I've got my qualified row here first, and that's my convention. Okay? It's an example of the kind of thing where you need to be organized. You need to do it one way. Not so good if you switch mid-representation, which I guess I'm sort of doing here, but okay. So how many people see what I'm doing, think I'm belaboring a point, and I should get on with it? Yeah, okay, good. How many people don't know what I'm doing and wish I would rewrite this game to match the other one? You guys are okay. Okay, good. Good. Glad to hear that. I hope. All right. The point is here, these are four different strategies. Okay? So now we need to put the payoffs that go with each of these strategies here. Okay. So if the superintendent plays this strategy and the community leader plays this one, the superintendent picks a qualified crony, and the community leader's strategy tells them to do a publicity campaign no matter what. Okay. What are the payoffs going to be here? Okay, that's right. -7 and -4 here. Okay. The superintendent's picking a qualified candidate. The superintendent's choice here is telling us what part of the community leader's strategy is going to actually matter. Okay? Because we're in the qualified row, the community leader is going to do the part of her strategy that corresponds to the superintendent's choice of a qualified principal. Okay? Down here, the community leader's strategy is the same, but the superintendent makes a different choice. Now, well, in this case, it's not going to matter because it's one of the strategies that is the same. The community, what are the payoffs in this case? -212, right? Okay, isn't it? This is the unqualified guy here, and there's a publicity campaign, right? This part of the strategy operating. Here, the superintendent chooses a qualified principal, and the community leader is playing this strategy. Okay? What are the payoffs here? Choosing a qualified guy, there's -7 and 4. They're the same, right? They're the same because this part of the strategy, what I'm, as the community leader, going to do when the superintendent chooses a qualified crony is the same in each of these columns. Okay? What about down here now? 5, -8. Very good. Okay. Down here, I'm choosing the unqualified one, And the community leader strategy now says, oh, now we're in the unqualified case, so no publicity campaign there. There's my -8. Okay. Marching along here, we're choosing a qualified principle. Here, the community leader strategy says no campaign for qualified, yes for unqualified. What are the payoffs here? Yeah, right. Superintendent's not trying to hire any cronies. Here, the community leader sees that, says, oh, okay, when the superintendent walks the straight and narrow, I don't need to campaign against him. It's 0-0. Okay. What about down here? I choose the unqualified. The community leader's playing this strategy. -212, right. I think I heard more than one thing, but I did hear the right answer here. Okay. This is the same payoff as those because the superintendent's making the same choice, and even though the community leader's strategy in column 3 has different actions for a qualified principal, it has the same actions for an unqualified one, so the payoffs have to be the same here. Okay. Here we have a qualified principal and no publicity campaign either way. What are the payoffs here? 0-0, good. Okay. And what about here? 5, -8, very good. Okay. Okay, so now I'm seeing that you guys are getting not only how to represent the strategies correctly here, but also how to figure out the payoffs. Okay? The fact that this game we're representing in normal form has a sequence is still mattering here. Okay? It's mattering in the number of strategies we have to consider for the second mover, and it's also mattering for us to figure out what happens in each of these cases. Okay? I presume that you're kind of seeing as we go along why we don't normally do this for normal form games. It's harder to set up this way. This way is much easier. Yeah. So outside of this one example, do it this way. Okay. But in this one example, what I want to do here is my goal with this example is to show what is the difference between Nash equilibria and rollback. Okay, there is a difference. Okay. So let's look for Nash equilibria in this game. All right, so is this cell a Nash equilibrium? No, right? Because if we're in this cell, if I'm the superintendent, I'd rather be down here. Okay, so no Nash equilibrium here. Is this cell a Nash equilibrium? Well, no. Here, if I'm the community leader, I can get a higher payoff there. Okay. This one, similarly, it's a negative there. That's getting a really bad pen, self-erasing pen here. That cell is not a Nash equilibrium because if I'm the superintendent, I can get a higher payoff here. What about this cell? This is a Nash equilibrium, right? Okay, so here's one. Think about that. We know in these games we can have more than one Nash equilibrium, so we're not done here. But people are kind of raising their eyebrows that this corresponds to a Nash equilibrium, but let's just look at it. If we end up in this cell, I'm the row player, do I have regrets? No, I'd rather have 5 than -7. I'm the column player, do I have regrets? Not really. I can't do better. I can do worse, but I can't do better. Was that what you were going to ask about, Kenyatta? Or? When I'm comparing for the column player, I'm only looking at the bottom cells because the column player can't control the rows.
No, like you don't look at the
For this cell, no, not for this cell. Okay. When I was looking at this cell, I did, and we're going to move up here now to this one. Okay, and I'm going to say, is this a Nash equilibrium? Where, well, let's see, 0 is better than -2, so it's looking good for the row player. For the column player, it's looking pretty good too. I can't do worse, okay? I can't do better, excuse me. I could do worse, I could do the same, but this is another Nash equilibrium here, okay? This one we know isn't, by the same logic that let us know that the 0 here is better than 2, so this one isn't. Let's keep going. This one, no, right? The superintendent would rather have the 5. But what about this one? Yes. Okay, it's another one. Okay, well, that's not what we got over here, right? Here we got one equilibrium. And throw away the booby-trapped pen. This one, where the superintendent chooses an unqualified, the community leader chooses no, no, this is one of our Nash equilibria, right? Okay. This one I'm going to call it number 1 because this one is the rollback equilibrium. Okay, right? That's what we predicted out of this game. No multiple equilibria here. We said what's going to happen is the superintendent is going to choose unqualified. The community leader's best strategy, their equilibrium strategy, is no, no. But over here, we have these two weird equilibria. And they are weird. Okay, let's now think about what they mean in words, and you will see just how weird they are. Okay, let's take this one first. This is the somewhat less weird one. In this equilibrium, the community leader says, superintendent, if you pick a qualified principal, you're off the hook. I'm not going to be in your face, but if you pick your crony, I'm going after you. Okay? It's an equilibrium here because the community leader's bluff is never called. The reason why this didn't look like the right choice in the sequential game here is that this part of the strategy, I'm going to label, this is a non-credible threat. Okay? This is a threat that the community leader might say they're going to make, but if we got to that point, if we got to the point where the superintendent actually chose the unqualified principal, the community leader would not want to stick to their strategy. Okay? It's a Nash equilibrium because in equilibrium, if the superintendent believes the non-credible threat, the community leader is not going to have regrets. Okay? So a limitation of Nash equilibrium, I think this is the first bad thing I've said about Nash equilibrium all quarter, it might be, but it is the biggest limitation of the Nash equilibrium idea, is that you can get Nash equilibria that rely on threats that would never be exercised if we got to that point. Now, if the superintendent believes that the community leader is going to play this, or the community leader is a computer program that's not strategic and is just going to do the strategy she's programmed to do, then the superintendent will indeed hire the qualified principal. The superintendent will respond to the threat. But a lot of superintendents, a lot of people in politics, a lot of people in all sorts of scenarios in life will say, she's not going to do that. Okay? She might say she's going to do the publicity campaign against me, but it would hurt her, and she'd get nothing from it. Okay? So rollback, the reason why we used rollback in the sequential games, and the reason why in all sequential games you use rollback instead of the broad idea of Nash equilibria is that rollback does not rely on non-credible threats. Okay? I'll write that over here. In rollback, your equilibrium strategy cannot contain non-credible threats, even off the equilibrium path. Okay? The reason why you get Nash equilibria that will have these non-credible threats in there is that they will be parts of equilibria where the threat's off the equilibrium path. We think in a lot of cases, non-credible threats don't affect strategic behavior. I might tell my kids that I'm going to ground them until they're 40 or something like that, but they don't really believe me no matter how horrible a thing they do because they know I don't really want them living with me till they're 40. Okay? There's lots of other punishments that I think most parents the world over threaten their children with in the heat of the moment. And strategic creatures that they are, the kids just see right past that, typically. Okay. This equilibrium also relies on a non-credible threat. It's even weirder. Okay? Usually some people will say, well, maybe this might really happen. Maybe your kids don't believe you when you bluff. But sometimes people can get away with non-credible threats. I think what I'm going to do is I'm going to say the last thing I have to say on this I'm going to finish it today. Then we'll be done with this and we'll start repeated games. Okay? This is the weirdest equilibrium ball. This is an equilibrium where what the community leader says is, if you hire the kind of principal I want, I'm going to do a publicity campaign against you. But if you hire the kind I don't want, I'm going to attack you. Okay? Why would the community leader ever do that? Okay? Well, it seems like a very strange thing for the community leader to threaten to punish the kind of behavior she wants and reward the kind of behavior she doesn't want. But if she's playing that strategy, then the superintendent will go ahead and make the choice she doesn't want. Okay? And she'll never be asked to punish the kind of behavior she wants. She'll never be asked to campaign against the principal that she wants. But this is not only a non-credible threat, it leads to a bad outcome. Okay? So if you might think that we might consider this happening, the argument for using rollback in sequential games instead of the full set of Nash equilibrium is really strong if you consider this kind of equilibrium. Okay? Last thing, just some language that I will use that won't take long. Just give me a sec here, guys. The more technical name for rollback is that it's a subgame perfect Nash equilibrium. Okay? And I just want to emphasize that the rollback equilibrium, the subgame perfect equilibrium, is a subset of the Nash equilibrium. Okay? So what we find when we do rollback is we always find something that is a Nash equilibrium, and it's a reasonable kind of Nash equilibrium. The kind of Nash equilibrium that rollback won't show us are the kind that are supported by non-credible threats, and most of the time we think that those would not make good predictions anyway. Okay, so there we are. We took care of that. We're going to start repeated interaction on Thursday.